So for those of you joining us this morning, we are, again, SPEAR, energy efficiency organization for Texas and Oklahoma. Typically at the beginning of our webinars, I will offer to do field training or meet your staff. Needless to say, we aren't doing any of that right now with COVID-19 and trying to flatten the curve and do our part to get this over with. So we will be ramping up our webinar presence. My goal is to provide 5 to 6 webinars a month. I know I was scheduled to teach a 6-hour class at Arlington BPI, and there were hundreds of other 6-hour classes. So there's code officials all across Texas and Oklahoma that, oh my gosh, what am I going to do to get my CEUs? Well, here at SPEAR, we're hoping to help that. This morning is a brand new presentation, but I will probably be running some reruns of our existing presentations. The reason I'll be doing that is just, again, to increase our webinar presence. I can't give ICC CEUs if you just go to our YouTube channel and watch it. There's no way for me to track that you've been paying attention and all the things that Zoom webinar tracks. I do encourage you to go to our YouTube channel. Actually, a handful of the best webinars on there are from our trainer this morning. He's already covered basically manual J, S, and D. There's no such thing as like for like. There's no such thing as a ton. Really great presentation style. Knows his stuff. And with that, I'll go ahead and turn it over to Alex. If you want to just introduce yourself and get started, the floor is yours, sir.
Sure thing. Thank you very much. If you have watched the other videos in this series, there is a little bit of new content here. But I should warn you that a lot of this stuff is a little bit of a retread of some of the things that we did in the other presentations. But a lot of the time, you know, when you have subject matter like this, where especially when it's involving, you know, pulling out root and branch the bad ideas and bad crappy rules of thumb that we teach as facts, and we teach as like, this is how things work in the HVAC industry, or in the building science industry even. Sometimes coming at it from different angles is not necessarily a bad thing. So hopefully this will be a good way to spend your time. So we're going to go over just a bunch of the bad ideas that have permeated the HVAC industry. And we're going to try to look at them from some different angles that sort of demonstrate why some of this stuff either can't be true, or some of the things that maybe is true, and we need to learn from the other side. And so one of the things, so that there's no such thing as a ton thing. So I've come up with a different way of trying to just establish the fact that a ton isn't 12,000 BTUs. So our first subject is going to be, how much does a BTU weigh? Because if there's a certain number of BTUs in a ton, I should be able to do some math and figure out how much a BTU weighs, right? If there's 12,000 BTUs in a ton, guys, a BTU weighs 2 2/3 ounces. Now, I want that to sink in as being the dumbest thing you're going to hear today, right? A BTU weighs 2 2/3 ounces. Like, that sounds ridiculous, or I hope it sounds ridiculous, because it is ridiculous. A BTU does not have weight, right? But if a BTU, or excuse me, if 1 ton was 2,000 BTUs and there's 32,000 ounces in a ton, then you take 32,000 ounces divided by 12,000, you get 2 2/3 ounces. There you go. That's how many that's how many ounces a BTU would weigh if this were real. And it obviously isn't, right? This is very obviously ridiculous, or at least it should be. So let's talk about what you might get from a ton. So first of all, when we talk about capacity of equipment, we talk about what a piece of equipment, what an air conditioner or heat pump is capable of doing in terms of its cooling capacity. What we're looking at right here is 3/4, actually. I had to cut off an entire chunk of the chart that I have for this. I had to cut off 3/4 of this, or excuse me, cut off 1/4 of this so it would fit on the slide. This is the capacity of a 3-ton system. This whole crazy chart, not AHRI conditions, not that number you look up off of AHRI. This is the capacity of a 3-ton system, the whole dang thing, right? And when we talk about AHRI capacities, when we talk about that all important number that all the codes reference, we're talking about capacities that are rated in a laboratory where the outdoor temperature is 95 degrees, which, all right, you know what? There's whole parts of Texas where that's close to being the design temperature, but there's parts of Texas that are much hotter than that, right? Which, by the way, hurts the performance of a system. But okay, 95 degrees, I'm going to give you that one, right? Like, that's a reasonable number. It's in the right ballpark for a lot of areas in the country. And even in lots of parts of Texas, that's close, right? South Texas, that's getting a little problematic, but let's say it's 95. Here's where things get terrible, right? Here's where things right off the bat, we should just be very, very wary of AHRI conditions, because they are running the return air temperature at a constant temperature in that return of 80 degrees. You know a lot of homeowners who keep the thermostats at 80 degrees, do you? Because I don't, right? AHRI is testing their conditions with an 80-degree dry bulb in the return. Now, they tested 50% relative humidity, right? Everybody's like, oh, great, 50% relative humidity. Yeah, not so great. When it's 80 degrees in the return, a 50% relative humidity is a 67-degree wet bulb. Now, that means the actual moisture content of the air is much higher than it would be if we were keeping the temperature at 75 degrees. Because as you know, relative humidity is relative to the temperature of the air, right? And warmer air holds more moisture. That means that they are testing this system with warm, wet air running through that system 100% of the time. So when they tell me that the capacity of this system is 33,600 BTUs, and by the way, AHRI only gives you the first number. This second number is something called the sensible heat ratio. That's how good this system is at removing moisture or controlling temperature. This tells me that 81% of this system's energy is going to be controlling temperature, and that 19% of that energy is going to be used to remove moisture at these conditions. And the capacity of this unit, this is a 3-ton unit, remember, is 33,600 BTUs, according to AHRI. So if we take this out of the AHRI laboratory, right, using, again, the real performance data, and we put it into, normal is in quotes here, we put it into normal temperature conditions. There's actually a power company in Tennessee called the Tennessee Valley Authority. They're more than a power company, actually, and some of you may have heard of them. They actually, a long time ago, they kind of caught wind of the games that they play with the design conditions for AHRI, and decided that, you know, they weren't going to play those games, and that in order to qualify for rebates and do things through the TVA, which is a very, very influential body in their area, that the manufacturers would have to publish data that they could access that told them what the capacity and performance data was at 95 degrees outdoor. They didn't have a problem with that. But with a 75-degree indoor return air temperature, which is much more normal, and the corresponding wet bulb number for 50% relative humidity, it's actually 62.5. Let's not split hairs over this, okay, guys? We're going to call it 63. And so 75 degrees indoor with a 63-degree wet bulb. So still 50% relative humidity, but actually less moisture in the system. And now the capacity of this 3-ton unit has dropped to 31,160 BTUs, right? Not 33,600. 2,500 BTUs, almost 10% of this system's capacity has just disappeared because we took it from the AHRI laboratory and we put it into more real-world conditions. And by the way, let's look at the percentage of energy that is controlling temperature. It's now 86%. Meaning only 14% of the system's energy is going to be removing moisture now, right? It's getting a lot worse at doing the job that I want it to do. In fact, it might be getting so bad that it won't do the job I need it to do, right? Especially in areas where we're bringing a lot of fresh air in humid climates like Houston and Austin. And so knowing what the real performance data is pretty important. If I look at So this doesn't affect you guys in Texas, but when we look at the 3-ton unit in, there are parts of the Northwest, there are parts of like Washington State and Oregon, where there are pockets of design temperatures that are actually below 75 degrees. There's such a thing as a 65-degree outdoor design temperature because you build the house with so much glass, it actually heats up the house. It's like if you had a 65-degree day, but you left your car in the hot sun, you get in the car, it's still hot in the car. And that's the solar gain, the radiant heat heating up the house. And so if this was the design criteria, I know it's a little weird corner of the world, but this 3-ton unit could have a 40,000 BTU capacity, 39,870 BTUs, right? Same unit, different set of conditions, right? If we go to all right, so this isn't quite West Texas. This is like, this is more like Arizona, Lake Havasu, things like that. But if we go to super hot outdoor temperatures with dry indoor conditions, right, the capacity of this unit might be 25,900 BTUs, right? 26,000 BTUs for a 3-ton unit. These design criteria, by the way, that's more common than you think, right? Actually, it's somewhere between here and here. So actually, it's somewhere between 26,000 and 28,000. But 27,000 BTUs for 110 degrees outside and in dry indoor conditions, yeah, I mean, that happens all over the place, right? This 3-ton unit is worth 27,000 BTUs in a lot of climates, nowhere near 36,000. And so the actual, what we can actually say about this particular 3-ton unit, not any 3-ton unit, is that the capacity is somewhere between 26,000 and 40,000, right? Like that's all I can say for sure, right? This system has a capacity somewhere between 26,000 and 40,000 BTUs. It gets an AHRI capacity, or when you get AHRI capacity, it's with an 80-degree dry bulb and a 67-degree wet bulb, which is just nuts. And under what are more normal conditions, and so if I apologize, guys, I probably should have customized this for Texas. Shame on me. I could have given you a quote unquote normal Texas condition. In fact, we can kind of look at it if we wanted to, right? So if we wanted to call it 105 degrees outside with a 75, 63 degree wet bulb at nominal normal manufacturer airflow, it's still below 2.5 ton. It's still below what we think of as 2.5 ton because there's no number of BTUs per ton. This 3-ton unit under these pretty normal Texas conditions, 105 degrees outside, 75 in the return, 63-degree wet bulb, 29,600 BTUs is the capacity of this system. And by the way, only 11% of the system's energy is going to be removing moisture. Yeah, have fun with that, Houston. That's going to be a blast, right? This is not a great matchup for that particular climate, is it? And if we think of this as being 36,000 BTUs because it's 3-ton, it's a terrible matchup. We're just not going to size this thing right at all. We're going to oversize it. It's going to have no moisture removal. It's going to be a nightmare, right? So where do we get the idea that there are so many BTUs in a ton, right? Where the heck did that come from? If it's not true, how did we end up with this idea? The answer is weird, but this is true. So before we had refrigerators, we had ice chests. Before we had air conditioners, we had ice melting systems. I couldn't find a picture of one, so this is going to have to do. It was the case before we had the refrigerant cycle, before we used what we now consider a traditional air conditioning system. We had particularly commercial buildings, but I recently found out that Thomas Edison's house actually had an ice melting cooling system in it. That you would replenish the ice in the system, and you had fans circulating air across the ice and blowing cold air through the building. Now, they were mostly designed for commercial systems, meaning the load really didn't change a lot when the temperature outside changed or the time of day outside changed, because most of these systems, the load was primarily internal load, right? Because you didn't just air condition an office building with an ice melting system. That just wasn't done. What they did is, they air conditioned manufacturing processes that generated heat and that kind of thing. And for that, they used ice melting systems. And so if you look at the math, when you melt 1 ton of ice, it absorbs 286,000 BTUs. It takes 286,000 BTUs to melt 1 ton of ice, right? So by the way, next time somebody asks how many, BTUs are in a ton, the right answer is 286,000 BTUs. I'm not kidding. Okay. And so the engineers, or not the engineers, the owners of the first air conditioner manufacturing companies, right? Your Willis Carriers, your Dave Lennoxes, they had to sell their systems to the engineers who designed the buildings, right? These I work for a company called MyTech, right? MyTech, I'm known for working for a division of MyTech called RightSoft, that predates us being owned by MyTech, but we're part of the greater, big family here. And MyTech makes all the metal pieces that hold together a building, truss plates and gang nails and joist hangers and all that stuff. And I can tell you one of the best ways to sell a product is to get the engineer who's designing the job to specify your product. And so the best plan of attack for a business owner who's got this new product is to target those engineers who specify what products. The guys who used to specify an ice melting system, we want them to specify this new magic electric air conditioning system. So those engineers have pre-existing habits. They're used to thinking of their cooling systems as being how many BTUs, or excuse me, how many tons of ice will this system need per day, right? A 2-ton system literally needed 2 tons of ice per day. That's what a 2-ton system was. It was an ice melting system that needed 2 tons of ice a day. That's what it was. And now we come along with this new fancy air conditioning system that produces BTUs, a certain number of BTUs per hour. It doesn't need to be replenished. So if you divide the 286,000 BTUs by the 24 hours in a day, you get 11,917. But we'll call that 12,000. And so the 2-ton product, the 2-ton air conditioner, was the equivalent of an ice melting system that needed 2 tons of ice per day. That's how we got the name ton. That's how we got the term ton. And the next time you're designing an ice melting system, or someone that you're working with is designing an ice melting system, that's when the term ton will actually mean something. Otherwise, it is ballpark city, right? The actual capacity of a system is something that you have to look up under real world conditions, because unlike melting ice, which always absorbs the same amount of heat no matter what the conditions, the refrigerant cycle is very much affected by the temperature outdoors, the temperature indoors, and the level of humidity indoors when it operates. It's also affected by airflow, but that is something that the designer is in control of. And so that has, that's less likely to bite you in the rear. So, like I said, slightly different animal than our no such thing as a ton thing, but the same lesson. And this is something that we talked about in that demonstration, right? Unless you're talking about ice, the number of BTUs in a ton is a big old question mark, and is something you need to look up. So this next one is another one that's near and dear to my heart, and we have an hour-long presentation on this, and you can go look up the YouTube video on this. We called the presentation Residential Duct Design is Backwards. But you have a lot of people out there, I'm sure I'm talking to some right now, who were taught that the proper way to size a duct is to use this thing, right? And to pick a number, right? And people are taught different numbers, 0.1, 0.08, 0.06. People are taught different numbers to quote unquote properly size a duct. Now, if you followed this rule, if this were correct, if 0.08, let's say, were correct, right? If this was the right way to size a duct, that would mean in all circumstances, if you wanted 100 CFM, you'd always use the same size duct, right? A 7-inch flex, right? That's what 0.08 says on my ductulator. I need a 7-inch flex duct for 100 CFM every single time. Yeah, okay. So let's think about this for a second. Do you get the same amount of air out of all these ducts? If all these ducts are the same size, right, and we used a smooth metal pipe, right, would you get the same amount of air out of it if you used another smooth metal pipe, but you made a shorter run? No, right? When you have to move the air further, it's going to give you less air. If you get a shorter run, it's going to give you more air, right? If you use flex duct and you don't change the size of the duct, you're going to get less air out of it. If your flex duct looks like this, hopefully it never looks like this, but even with a small bend in it, you're going to change the amount of airflow. And here's a big variable. What if the fan is more powerful or less powerful? Not every 3-ton blower it has the same horsepower or the same size cabinet or the same configuration that causes the same amount of airflow to come out. That's not how that works, right? There are wimpy fans out there and there are powerful fans out there. And that's absolutely going to change the amount of airflow in the system, right? Of course, these things are not all going to be the same, right? And then we start taking into account what happens when you put filters in here and coils on here and other things, right? When we think about, and this is, I like to do it when I'm dealing with HVAC contractors. I like to say, if it was somebody else's job, you would look at it and be like, oh yeah, there's not enough air coming out of that, right? But all of a sudden, if it's yours, every 7-inch duct gives you the same amount of air, right? And that's not true. Right? Long runs, the ones that are further away from your system and have to go through 4 Ys just to, hopefully they don't, but have to go through a bunch of crazy connections to get to their destination, they're going to have less airflow from the same size duct as something that home runs right off the plenum, right? Which, by the way, is why people buy our little software program here to help them calculate those sizes and to figure out what they're going to be, because it's not always going to be the same friction rate. It depends on way too many variables, right? One of the biggest variables in that process, by the way, the filter, right? And we all know this story, or most of us know this story if you're involved in HVAC. The homeowner goes down to the big box store, right? Because they're going to save money. They don't want to do the maintenance call or the maintenance appointment. They're going to put their own filter in. So they go to the big box store and they ask the guy at the big box store, hey, what's the best filter you guys have here? And if they're lucky, they remember what size, or they brought the one in that there was on their unit. And the big box store guy says, this is our best filter, right? It's the Fan Killer 5000, right? And the Fan Killer 5000, it's MERV 1,000,000. It stops all of the particles, right? But who cares about pressure drop? And so they go and they buy a MERV 13 1-inch pleated media filter, and they put it in their system and murder the fan, right? Because they'll tell you that their filter stops small particles. They forget to mention air is a small particle, right? And so next thing you know, the airflow has been reduced so much that the coil freezes up. Now the air conditioner isn't working. They call their HVAC contractor, say the air conditioner isn't working. And lo and behold, it's because we put in this crazy filter. But here's the thing. The company that makes this filter, they sell filters to the HVAC contractors too, right? There's such a thing as the Fan Killer 5000 Pro, right? And not enough people are checking the specs on the filters, the high-end filters that they sell, and taking it into account, right? I can sell a high-efficiency filter, something that creates more restriction and makes it harder for air to go through. It's okay to do that. But if you don't adjust something else, you're just going to get less airflow. If you adjust something like fan power or duct size, right? Instead of using a 7-inch, maybe I need to use an 8-inch on 100 CFM. That is possible, by the way, and legal. It's okay, right? The books say it's okay. And it's what you have to do if you're going to put a bunch of extra restriction on the system somewhere else. And so the real catch is, though, the real bugger here is the fact that you can be doing your due diligence. And some of these filter manufacturers, they're tricky little buggers. They know that their filter kills fans, right? It's the Fan Killer 5000. They're aware of it. And so they put somewhere in a little tech sheet somewhere that the pressure drop is only 0.1. right? It's always 0.1, by the way, 0.1 and 0.08. When you get these murderous filters, they're always rated, quote unquote, rated at 0.1 or 0.08, right? That's not a coincidence. Okay. I'm a bit of a conspiracy theorist, full disclosure here. I own a tinfoil hat. When I see something, messed up in the world, I go looking for the giant company that's ruining it. And this is a situation where I really do believe the manufacturers are a little out to get us. Not all of them. There's plenty of filter manufacturers that do a really good job, right? Here's how you can tell the difference, by the way. When you see that they have a pressure drop on their filter and it's not a filter grill, those get a pass, and I'll explain why in a minute. But if you have a central filter, a cabinet filter, right, that goes on a filter rack by the unit, if it tells you that they have one pressure drop number, they only give you one number, that's a red flag. Now, it doesn't necessarily mean that they're playing with the data, but it becomes a possibility because when they give you one number, what they decided that they did for that one number is they chose what the velocity was through that filter, right? Now, I like to take Honeywell as an example. They're a big company. They make a quality product, and they do only publish one number for some of their filters. They actually have chart data available. It's just a little hard to find. And they don't provide a chart. They actually provide a curve, a graph, but it is out there, right? But most of the technical data you go looking up for Honeywell, it just gives you like one pressure loss number. Now, to their credit, Honeywell uses the ASHRAE standard for velocity of filter ratings. The ASHRAE standard for the velocity of rating of filter is 492 feet per minute, which is awfully specific, but it works out to be the velocity at 1200 CFM at standard 3-ton orifice, which I don't remember off the top of my head, right? But it's basically based on, the velocity you get at a 3-ton, your typical 3-ton cabinet, right? And so they rate it 492 feet per minute. Some manufacturers, they actually just say 500 feet per minute, round it up, also fine, right? Now, if you have a 4 or 5-ton system, your velocities could be higher than that. And so the pressure drop numbers might actually be higher than that. But if you have a 2-ton system running 700 CFM, you might find that the pressure losses are lower than what they're published, which not your biggest problem, but technically when you're using one number, that's the risk you run, right? There are other filter manufacturers, and I will not name names. Ask me all you want. I'm not going to do it. There are other filter manufacturers who will publish are, 0.1. And if you read the fine print, they're getting that 0.1 inch pressure drop. I have seen filter manufacturers rating that pressure drop as with as low as 200 feet per minute, which is well under half of what the typical velocity would be through a filter. So what's the problem with that? The highly restrictive filter that has air moving through it very slowly is no longer highly restrictive. But as you move more air through that same filter, right? It's, 10 pounds of stuff in a 5-pound bag, right? You are trying to squeeze more air through it than it's actually designed for, right? And so the pressure loss numbers go up, and they go up faster. So in other words, if they tested their filter and its pressure drop is 0.1, and it's always 0.1, because they're always running 200 feet per minute through there. If they move the air through it at 400 feet per minute, they double the velocity through it. What do you suppose happens to the pressure drop, right? Does it go to 0.2? Nah. It goes to like 0.2 and a half, 0.25, 0.26. Because everything about airflow is on a curve. And that curve is always more steeply going up, right? And so when you put it in a real world situation, this filter that says it has a pressure drop of 0.1 right on the box, actually in the field has a pressure drop of 0.25. And that may sound like a small difference. Here's a little tip. Whenever you're dealing with numbers like this, it's always a good idea to think about them in terms of the percentage change, right? So rather than look at it as you know, oh, well, that's only a 0.15 difference, because 0.15 can sound small. That's 150% increase. That sounds a lot bigger. And that's what it is. It's a 150% increase. Or it's another way to look at it is it's an increase of about 30% of the total fan power available. About 30% loss of fan power just by adding 0.15, because most fans are rated at around 0.5 inches of static, although that's not a given, and we'll talk about that a little bit later. And so you got to watch out for those filters. They'll be printed right on the side of the box. Oh yeah, 0.1 pressure drop. Actually, if I only see one number, it makes me very suspicious, and I go digging. And you will often find that they're a lot more restrictive than the published numbers say, right? Because they're messing with the numbers there. So the myth here is changing the location of the unit doesn't have too much of an impact on the design of the system. It should. It has a massive impact on the performance of the system, actually. But this 0.1 way of thinking often tells us, I'm always going to get 100 CFM out of a 7-inch duct, right? Like, that's not even close to being true. And, we've got it drives me nuts. Sorry, I'm taking a moment of I'm going to vent here for a second, because, the plumber and the electrician have to navigate through the house with components that, for the electrician, it's the diameter of a conduit, right? It's like, what is that, 3/4 of an inch or something? Or if you're a plumber, the biggest thing you have to route through the house is, maybe a 4-inch drain pipe or something, or vent stack. And the fun fact about that is when the architect designs the building, they plan for it, right? They create space for it in the design of the home, right? But the HVAC system, we designed the home, then we handed it to the HVAC contractor and said, now fit an HVAC system in there somewhere, without having done any calculations or sizes, without knowing if they created enough space for it. And when the HVAC contractor comes back and says there isn't enough space for it, and we need to change your beautiful building, they get a lot of resistance and pushback, to the point where they may find someone else to do the job, when the right answer was, this needed to be a bigger space, right? And a lot of architects are moving the mechanical room to the perimeter of the building, the corners of the building, right? Because they don't want it in the way. Guys, we put the unit in the middle of the house because it was going to perform significantly better from there than it would in the corner. And again, 0.1 thinking, right? It's like, oh, well, you always get the same amount of air out of this size duct. So who cares? I'm just going to move it over there and we'll just run some more duct for it. Yeah, that's not how this works. Right. So some of you may not have any background in electrical or anything. This might not make a lot of sense, but this presentation was geared toward, more people in the trades. And you might remember this from high school physics, right? Or shop class or something, right? When you're doing when you're doing anything, resistance adds in series, not in parallel, is the rule, right? This is actually true in any flow, whether it's a flow of electrons, or it's a flow of water, or it's a flow of air. Resistance adds in series, not in parallel. So if this is my power source, and I have a circuit that goes through 2 resistors like this in one big loop, you add these 2 together when you're calculating the resistance on the power source. It means the flow of electricity will be impeded by both of these together, right? And so you're going to get a lower flow of electricity. Here, in this example, I have a power source and 2 separate circuits, right? Even if these resistors were the same, you don't add them together, the same as in this one. You don't add them together. You take the higher of the 2, right? Because this is one path and this is a separate path, okay? These don't add together when you have parallel circuits, okay? And this is the thing that's going to affect our duct systems. So if I had the world's simplest duct system, it's a 2-ton, 800 CFM duct system, and every outlet's 100 CFM. So that's never going to happen, right? But let's just take this as an example, because it's good to equalize the numbers so we can see what happens here. When I start in the middle of the building and work out, right, it turns out I can use 7-inch runs on all my 100 CFM registers. I get 10x6 going each way and a 16-inch return. Cool. The loop, the circuit that this air is traveling, It's coming down here, coming down here. That's the longest circuit in the whole thing, by the way. Now, technically, it comes back here in a more direct path, assuming there aren't like doorways and stuff. But when I drew this as a little bow tie shape, people got confused. So I'm going around to show you the size of the loop. This is the loop. This is the circuit. This is the parallel path that the longest flow of air has to take right here. Okay, that's how it's shaped. It's a pretty small loop, pretty tight shape. Move the unit to the corner and have to run the trunk like this. And I know a lot of your stuff isn't trunk and branch. I'll show you an all flex one in just a sec. Now my air has to go this way. Now look, right? 7, 7, 7, 8, 8, 8, 8, 8. The air has to work a lot harder to get all the way down here. And so to get the same amount of airflow out of these, I need 8-inch runs, right? And by the way, that 16-inch return haven't changed the airflow. Still 800 CFM. Now instead of 16, it needs to be 18. Why? That's why. Because now this air has to travel this whole path, right? And by the way, not just the length of the path, but extra turns and twists in the process, extra fittings and places where restriction happens in the process. And it all adds up. And what would happen if I put all 7s here is I would get less air out of these runs than 100 CFM. And I would get less air. If I put a 16-inch here, I would get less air than 800 CFM, right? Now, well, what if I was using a variable speed fan? Okay, cool. So now you're just going to murder the fan. Awesome. It's going to sound like a jet engine. It's going to last 5 years, and I'm going to have to be replacing that $2,000 ECM motor. Whether or not it's under warranty is a moot point. It's not going to be good, right? So in order to get the same airflow from a more difficult path, I'm going to need to upsize the size of the ducts, right? Because otherwise it won't work. Otherwise, I just get less airflow than I'm designing for, right? If you use that 0.1 mentality, that 0.08 mentality, you'd use the same size duct here and the same size ducts all here and here. And you'd end up using smaller trunks too. That would be 20 by 8. That would probably be 14 by 8 and so on. And what you would get is like 700 CFM instead of 800. And if what makes this system work is 800 CFM and you're not giving it enough, you get bad performance. It's actually this kind of thing, right? Because we take it for granted that 0.08 of the ductulator is how airflow works. This is the kind of thing that makes contractors not trust load calculations, right? Because it turns out, they tried to do a load calculation. They believed, they put their trust in a load calc and it said they needed a 2.5 or 2 ton system. And they put in a 2 and they thought they were pretty sure it needed a 2.5, but they put in a 2. When they put in the 2, they didn't do this, right? The architect moved the unit over to the corner and they went 7s all the way down here, right? And they went 20 by 8 and they went 14 by 8 and they used a 16-inch return and the thing didn't work. But they didn't identify that as an airflow problem. They identified it as a sizing problem, right? And now they don't trust manual J when it wasn't the manual J. It was their lack of using manual D that caused the problem, the airflow calculations, right? Because they paid money. Because I paid money once. I went to a class. When I first started doing this, I went to a class and paid like $100 out of my own pocket to learn duct design. And the jerk taught us, dial in 0.08, and that's how you size ductwork. I paid money to learn that, right? And at the time, I believed him because I wasn't the head trainer for Wrightsoft yet. And then as I worked for Wrightsoft a little bit, I realized, oh, yeah, that's not how it works at all, right? That's not how you do things. But so many people are taught that at trade schools and in classes that they believe it. And so they think this looks wrong. And it turns out this is what you need to get that airflow because the air has to work so much harder. And the same thing does happen with flex systems. Now, I realize that no flex system looks this perfect, but no trunk and branch system looks as perfect as the one I have there either. So, but 977 for everything. Again, 16-inch return. Now, if I move this unit to the corner, right, and here's my loop. If I move this unit to the corner, though, now I'm at 1088 over here at the end of the run. Now, it actually turns out to still be a 16-inch return. So this didn't add quite as much restriction as adding a couple of extra elbows did in our other design. But it went from 977 to 1088 in some of these options, right? Now these stayed 7s, right? But this is how we resize this system here, because again, it increases the loop. It increases the distance traveled, and the number of components encountered along that path. Okay, and where people have, this is my next slide is one of my favorites. I squeeze it into anything where I'm talking about duct sizing, because the number of folks out there who are like, relax, dude, it's a 7 or an 8, right? It's an inch. Who cares? It's just like 1 inch. It's a 6 or a 7. How much difference could it make? Yeah, something's coming. A lot is the answer to that, right? A lot. Because it's not a 6 versus a 7. It's not a 7 versus an 8. It's a 28 versus a 38. It's a 38 versus a 50. It's not about the diameter. Air does not travel around the edge of the duct. It doesn't travel around the diameter of that's the perimeter, but it doesn't travel around the circumference when it's a circle. It doesn't travel around in a line through the middle of the duct. It travels through the whole duct. The area of that circle that duct makes, right? And I know this rectangular ducts, or the area of the square, whatever, is what the air is passing through, right? And so when you go from a 7 to an 8, you're not going from 7 to 8. You're going from a cross-sectional area of 38 to a cross-sectional area of 50. Now that's a much bigger jump, right? Would you say that, oh, who cares, it's 38 versus 50? And this is my favorite. When I go to areas that people just don't use 7-inch duct, right? I'm actually okay with people not using 7-inch duct if they put balancing dampers and everything, right? Particularly in their 8-inch ducts. Because when you're not using balancing dampers and you're using 6s and 8s and you're not using 7s, you're using double the size, right? You're doing surgery with a sledgehammer here, right? It goes from 28 to 50. That's the area. That's the jump. It's not quite double, but it's close to doubling in size when you go from 6 to 8, right? One of the ways that I like to, sometimes I'll like pop quiz people when I'm talking with, like I've given presentations to like installers and techs, and I try to make it a little less mathy for them. And I'll ask them, how many 6s does it take to make a 12, right? And not everybody's, but a lot of people's first guess is 2, right? And so the math works out that it is just over 4. So the answer actually is 5, right? 5 6s make a 12, right? 4 is a really good guess, but it turns out that the extra restriction of the smaller duct means that it probably needs 5 6s to make a 12, because it's about the area, right? The square inches, not the diameter, right? So the next topic is a bit of a hard change in topic, but it's about the importance of looking things up. I am somewhat involved with the HVAC School podcast. I've done some episodes for them, and that group over there, I'm sure they didn't make this up, but it's where I picked it up. There's a saying that they have, or they don't have, but is around the industry that they use a lot over there. It's RTFM. It's an acronym, and we will censor this. We'll pretend that it stands for Read the Fantastic Manual. I think we all know that the RTFM does not stand for Read the Fantastic Manual, but that'll do. And the reason you always want to read the manual is because they're always making things cheaper and worse. At least that's why I would always read the manual. That's my opinion, is we're always looking for ways to make things cheaper and worse. And we find them all the time. So not all two-stage systems are created equal, right? I know folks who will look at it, look at a problem area and be like, oh, you know what? We need a 2-stage for this. That's 2-stage is going to fix this. 2-stage is going to be a big improvement here. So improvements have been made in this, right? This is some data from Copeland Scroll, and I actually talked to the guys over at Copeland. They're like, oh yeah, that's one of our older models. It's still in production, but it's being phased out with newer models that are better than this. But it turns out that most of these products operate at about between 62 and 67% at low stage, right? So when you look at the low stage of a two-stage unit, you're most of the time looking at something like 60%, 60 to 70% of the capacity. But there are some two-stage products out there that at 2 ton, instead of being a drop to 63% at low stage, it's a drop of 78%. It's not much of a drop, right? Or even 80. I've seen 80%, right? And so now all of a sudden, the low stage of a 2-stage unit is bigger than a 1.5. You know why we put those in, right? Is so that they'll run longer. Well, if low stage is bigger than 1.5, the 1.5 would have run longer. Uh-oh. Right? If you don't look it up, you don't know, right? You've got to look up what the data is, right? Because if you just say, oh, it's a 2-stage unit, it'll be fine. There are models out there that will modulate all the way down to like there are dual compressor models out there that modulate down to 50% at low stage, right? They're more expensive, but they're out there. And then there's a lot of them out there that do this sort of 60 to 70% all the way across the board, including the 2 ton. And there's a couple of them out there that don't do so well. So look, this is not saying that this product is bad or that 2 ton 2-stage is bad. That's not the takeaway here. Sorry, I jumped ahead. The takeaway is look it up, right? So the takeaway is RTFM, right? You got to look at the manual and figure out what the heck this thing is doing, right? So yeah, we've talked about how there isn't 12,000 BTUs in a ton, and that if you're in a meeting with the right soft guy and we're talking about myths, we are definitely going to talk about square footage sizing. So yeah, I've heard a whole bunch of things, right? 350 per ton, 400 per ton. Some of you maybe seen this one before. I'm told that this was not created as a joke, right? You cut this out and stand a certain distance away, and this is 1 to 2, this is 2 to 3, 3 to 4, or 2.5 to 3.5, and this is 4 to 5. Supposedly somebody created this a long time ago and was using it with a straight face. Although it's gotten a lot more usage as a joke than it has as a real thing, I hope, because this is BS. And take the age of the home, divide by the climate zone. I don't care what weird rule you have, do a load calculation, because all this stuff is bunk, right? If I go and I look, let's think about this for a second, right? Why are we using floor area to calculate load? Most of you guys are in Texas and Louisiana, in that area. How much slab construction do you have? A lot, right? You know how much heat travels through the slab in the summertime? 0 BTUs. The cooling load on a slab is 0 BTUs. Yet here we are looking at square footage of floor area as the determining factor in a load. It literally doesn't matter. And we're using it as the determining factor of the load. It has 0 impact on the load. But everybody goes, oh, let's look at the floor area where no heat transfers as our standard for sizing a system. Square footage of the floor means nothing to what the load is on a slab house for a cooling load, right? And when it's pier and beam, the crawl space is pretty cool, right? And it's still not a huge impact on the load. In cold climates, walls are your big one, because there's so much area and so much delta T, right? In hot climates, your ceilings and your ducts are going to be a big factor, right? That's a poorly insulated ceiling right there. Is going to have a lot of heat transfer there. And windows are a big one everywhere, right? Windows are probably between windows and maybe ducts, depending on which one is worse. Those are going to be your biggest 2 contributing factors to most cooling loads, particularly in Texas. Yet nobody's square footage rule figures these things in, right? So I'm not bitter or nothing. So we're going to look at this 2 different ways. We're going to look at this, and I'm going to disprove the whole square footage thing. So if there's anybody who's like, but, kind of, doesn't it matter a little? No, it doesn't. Stop thinking that. And I want to show it to you 2 different ways. So for those of you who are math kind of people, this will hopefully resonate. So we're going to take two very simple examples, but you can scale this up to a bigger house. I just like to keep the numbers small so we can wrap our heads around it easily. If you had a square that was 1 foot square, right? 1 foot cube, actually, a cube, but 1 foot cube. So it's 1 foot by 1 foot by 1 foot by 1 foot by 1 foot tall. You could take the surface area of that, and each of those surfaces, floor, ceilings, and walls, are going to be 1 foot, 1 square foot. And so that's going to be a total surface area of this shape of 6 square feet. So that means for every 1 square foot of this, there's 6 square feet of total surface area, right? But if I made this building 5 foot by 5 foot, right? And I make it 1 foot tall so that we don't lose the, this would be cube square law, but buildings don't get that much taller, but they do get a lot bigger. The footprint gets bigger, right? And if I look at this, then this wall would be 5 square feet, so 1 foot tall by 5, and this wall 5, this wall would be 5, this wall would be 5, and the floor and ceiling would be 25 apiece, right? A 5 by 5 foot square. So for every 1 square foot of this, there's only 2.8 square feet of surface area, right? There's 25 square feet of floor and 70 square feet of total surface area. That means for every square foot of this, I have half as much, less than half as much square footage of exposure than I do for this one, right? Here's another way to look at it, okay? You see these squares? These are all somewhat similar to this one because they have exposure. But you see these, right? This 9 square feet here in the middle, right? This 9 square feet in the middle has no walls. It has no windows. It has ceiling and floor, but that's it. It's all interior, right? There's no way for there to be load on this except from the ceiling and the floor, right? So here's another way to think about this. If you are a dyed-in-the-wool square footage rule guy, and I can't shake you from that, or I haven't shaken you from that, let me try one more way to shake you from it. I want you to, in your head, picture a 2-ton home. It doesn't have to be this home, right? This is, by the way, a real 2-ton house. Did the load calculation and everything. That's a 2-ton house. This house needed a 2-ton system, okay? I don't care what size you think this is, right? You make it as big or as small as you want. Just make it a rectangle in your head, okay? So the shape has to be a rectangle, right? We're going to keep it a nice, simple 4-corner shape. So I've got this 2-ton house here. Now I've got 4. Okay. And each of these is still a 2-ton house, right? So I put them 4 by 4 in a grid. That's a 2-ton house, and that's a 2-ton house, and that's a 2-ton house, and that's a 2-ton house. I'm assuming there's enough space between these houses that the sunlight can get to the windows. Okay. Smush them together and make one big house. What's happened to half of the exposure? It's gone. So all of the load that I got from all of these windows here and all these windows here and all this wall here and all this, it's gone. You're not going to have 2, 4, 6, 8 tons when you do the load calc on this. This is a 5-ton house. Yeah. So square footage rules straight up don't work. There you go. So here's another, it's a bit of a random one, but you get a lot of this, actually, a lot of information going around about this, that somehow, some way, some reason, we need to be worried about the velocity in the duct, right? When I show an 8-inch duct on 100 CFM, people are like, no, that's not enough velocity. And I taught my instructor taught me that you have to, nope, that's all BS. Nope, doesn't matter. So you can actually have too low a velocity in the duct. If your velocity gets real low, and I mean real low, you can make the surface of the duct cold enough that it starts to sweat. Okay, that's why there's some minimum standards for duct size, or actually maximum duct size. Basically, they're not maximum duct size; it's a minimum friction rate. 6 to 1, half dozen the other. But there are some minimum standards. There is such a thing as a duct that's too big in manual D, but 8-inch on 100 CFM is not it, right? So if the velocity in the why doesn't the velocity in the duct matter? I thought air mixing was important. It is. It's just that the velocity in the duct doesn't affect that. Okay. So here's a little mental exercise for us. Here's an even simpler duct system than one we were looking at. Now here's what I need you to imagine. This is very important. These grills are the same size. Okay. This is important. You want to know what the velocity of the air in the room is going to be and what's going to affect the room comfort. It's the velocity of the air coming out of the grill, not running through the duct. And so I want you to consider these grills to be the same size. Okay. I don't know what a common size would be in your area. Let's say 10 by 6. Okay. So both of these grills are 10 by 6, which is probably a little too big for 100 CFM, but that's okay. So if I have a 10 by 6 grill here and a 10 by 6 grill here, I'm going to need to attach that grill to a boot. And here's where people's brains start to break, because they may have a 10 by 6 by 6 boot. They may not make in your area or have available at the distributor a 10 by 6 by 8, right? That's just not a part. Now, you know, they could make that, right? Like we'll make that for you all day at MyTech. You want it? We'll make one for you, right? But they don't sell it at your distributor. So what am I supposed to do here, right? I need this to be a 10 by 6. Use a reducer, right? Do an 8 to 6 reducer. If 6 is the smallest one they make for 10 by 6, and I doubt it, they probably make a 10 by 6 by 7. You take the largest boot you can, and you use a reducer right there at the end. And now you can have the same grill size with these two different duct sizes. Now, if you just put in a 6 on this one and an 8 by this one, and you didn't do anything else, what would happen? Well, of course, you'd get more air out of this one. And because you got more air out of this one, this wouldn't be 100 CFM. The split would be, 130 and 70. And so, of course, the velocities would be different. But what if I put a balancing damper in here? Same size grill, 2 different size ducts, but I'm going to take a flow hood, and I'm going to test the airflow in here and test the airflow in here, and I'm going to close this damper, and I'm going to test it again. And I'm going to keep doing that until I've closed the damper exactly enough so that I get the same airflow out of these two grills, 100 CFM. We know you can do that. Close the balancing damper. You're going to get less air through here. So what's going to happen is that 100 CFM, that's a very doable thing. Close the balancing damper, leave it open over here. These will both get 100 CFM out of the same size grill, same airflow, just 2 different duct sizes. And so the air moves up this duct a little more quickly because it's a smaller duct, and it comes out of this grill. The air moves up to here more slowly, but it gets to the end there, and it hits that reducer, and the air speeds up. There you go. And once that air speeds up, it's going to speed right out. The same grill face, the same area, the same airflow means the same velocity. And so velocity in the duct doesn't affect room comfort unless you let the size of the duct dictate your register sizes. Yeah, you shouldn't do that. You should size your registers for airflow. And if the size of the duct it takes to get that airflow doesn't match conveniently with available parts, get creative. But size your register for the right airflow, size your duct for the right airflow, and connect them however you need. And you will get the right air velocity in that space. Because the air velocity in the space is only affected by the register. The duct will be sized for whatever size you need to make it to get that air there. Because this could be a damper, right? Or it could be a super long run with 5 elbows. Whatever it is, if there's restriction getting the air from here to here, you might need a larger duct to get that air. So get it. As long as you size the grill right, room comfort won't be affected. Okay. And that's right in the manual D, by the way. How about this one? Thermostat location, right? They teach this one all the time too. They say the register is going to be, or we're going to locate the thermostat in the hallway, right? Only this is the customer's favorite seat in his house right here. He's got a couch right there and he watches TV against that wall. And the thermostat being out here means that when the house starts to heat up, heat is going to start to hit this person, radiant heat. Right? Don't tell me, oh, well, the return in the hallway is going to draw back the air and mix the air. First of all, returns don't suck. The velocity of the air from this spot until it finally gets to the return is real slow. But Also, it's going to be an average temperature, averaging this part of the house where radiant heat hasn't really heated things up yet. And so the swing in temperature between these spots can be pretty significant because radiant heat operates by line of sight. By the time the heat actually gets to the thermostat, we're pretty warm over here. And we're in a we're in a situation where the temperature is going to swing up and down more significantly. The thermostat probably belongs on this wall here, in line of sight of our heat. The thermostat belongs in an occupied space, according to the ACCA manuals. Nobody hangs out in the hallway. Long story short. So this one, there's a myth that all fans are rated at 0.5 CFM, 0.5 inches of static pressure for nominal CFM. It's just definitely not true. You can look it up. There are 2-ton systems that are rated at much higher. There are 5-ton systems that are rated at much lower. This does tend to be the pattern. As you go up in tonnage, you tend to lose pound for pound or CFM per CFM power because cabinet size is shrinking, right? No, it isn't. 5-ton units are bigger. Yeah, but they're not proportionally bigger. If you compare a 2-ton unit to a 4-ton unit, you haven't doubled the size. And so all of the velocities go up through the cabinet as you're going up in tonnage. And so that creates more restriction and generally gives you, on average, less airflow pound for pound, right? But you do have to look it up because different cabinets are designed differently. There's no rule of thumb for coils, and we've already done the filter thing, right? Those are the Honeywell curves I was talking to you about, right? It's not a straight line. As you go up in pressure, this goes up, right? So, this ranges, I'm not kidding, by the way. Pressure drop can range from 0.05 to over 0.4, right? They shouldn't sell that filter, by the way. The chart, when it says 0.4, it should say, just don't use this filter here. And the whole residential duct design is backwards thing, we've talked about it, right? You don't start with a friction rate. If you start with a friction rate, you have to end by changing your fan. That's how friction rate design works. So if somebody very knowledgeable and very respected told you point one of the ductulator is how to design a duct system, it is how you design commercial duct systems. You pick your friction rate, you design your system, and at the end of the day, you pick a fan that can handle the restriction you created. Something has to change. If you don't change anything, you're not in control, right? So am I going to change my duct size or am I going to change my fan size? Well, in residential, I don't have interchangeable motors and pulleys like I do in commercial. So in commercial design, you can pick a friction rate, figure out how much resistance that all creates, then choose a fan that's going to work, or choose a fan configuration that's going to work. In residential, this is what my fan can handle. That's it. This is what it can do, right? This is the maximum, static pressure I'm allowed to operate it at, right? If I put more pressure on it, bad things happen, which means I have to work backwards to figure out how much resistance is on this fan and then find a size of duct that's going to make the fan work, right? You don't start with 0.1, you work backwards to find the right size. And it might be 0.1, it might be 0.08, it might be 0.06, or it might be below the minimum. This is the minimum, by the way, 0.06. And you might actually have to change something about your duct design to make it work, because you can't just keep doing the same thing over and over and change everything underneath it, where you put the unit, what filter you're using, what coil you're using, what fan you're using, and expect it to work. Okay, so I'm sure I've kicked loose a bunch of questions. So that's the end of the official presentation. Last time we did this, Jason, you were sort of my question moderator. Are we still going to do it now?
Yeah, I'll be your moderator again. And if you don't mind, I'm sure one of the questions is always, can we get a PDF of this? And then
yep,
a verbal okay. I've got to steal. I love your surface area, not floor area graphic, the 1x5, because I am a math guy.
Yeah.
And it's like, I'm going to steal that slide. I'm just warning you right now.
Help yourself. Help yourself.
Right, okay, so let's go with the questions. At what velocity are you using for trunk and branch supply and return?
You don't size with velocity. You size to, this is manual D, finds the proper amount of, tell you what, check out the residential duct design is backwards YouTube video that Jason has, that Spear has, and it will walk you through what the process actually looks like. But you don't use velocity to size the system, you use pressure, right? So a more powerful fan, you can use smaller ducts and higher velocities, unless you run that duct a country mile, use a massive filter and a highly restrictive coil, in which case you don't have the power to run higher velocities. You're going to have to use lower velocities. You adjust your duct size and therefore your velocities based on fan power and what you're asking that fan to do. The more you ask the fan to overcome, the lower your velocities are going to need to be, so they create less restriction. The less you're asking your fan to do and more capable your fan is, the smaller my ducts can be, because my fan can handle that and will use higher velocities. At the register, the velocities that I want to target, which I now realize is probably your question. I apologize for that. I should have seen that. My bad. But at the register, you use a velocity that gets appropriate throw and air mixing. And that depends on the size of the room a bit. So I know I'm going to go to a blank desktop here, but that's because I'm going to just show a quick
and just for those of y'all
so,
still on the webinar, in the next 6 weeks or so, I do plan on rerunning all three. I don't want to take 3 more hours of your time, Alex, but I do plan on rerunning those webinars you've done for us. I hope to get you on for the Q&A at the end to give us 10 minutes, but if you can't, I'll do my best of winging it and then give your contact info.
No, I've probably got the time to do that. Okay. But if I look in a register book, like, it tells me what my throw distance is going to be and the spread of that is going to be when I look at a particular grill at a particular airflow. And so depending on the size and shape of the room and the number of registers I might put in it, it's a variable, right? So a big, large room with not needing a lot of air because it's facing north, I might use a higher velocity, whereas a smaller room with a big window in it facing west, I might be able to use a much lower velocity because I'm not covering as much space. So it is a variable. Generally speaking, though, there is actually, if I open that up, and this, by the way, is not an ACCA manual. This is just the catalog from Hart and Cooley. Shoemaker has something similar, and it does give recommended 500 to 700 feet per minute for residences, right? So like, they have this. I don't even need an ACCA manual. I can just read the grill manual and it will give me some recommendations there. But there is a range. I would say actually 400 to 750, but you know what? These are the grills you're using. Do what they recommend. That's a pretty good piece of advice.
That's I like that read the manual acronym. I've had over 700 HVAC contractors in person, just kind of a HVAC 101, a real basic class that I've been teaching. And at every single class, I ask them, so who's read the manual on the last air handler they installed? I've yet to have one person raise their hand. And I can't tell you, as a building official, how many homes that you go up into to give a CO on. You're up in the attic, and the manufacturer's installation instructions are still sealed in the plastic bag in which they arrive. They don't read those things at all.
Yeah.
A few more questions. What are the Manual J inside design temperatures, and why? And aren't we required to adhere to Manual J sizing equipment per code? Yes, you are required to adhere. I know the Manual J is a little bit different. People get the energy code setbacks confused with what the Manual J requires. Do you want to talk about that a little bit?
So Manual J doesn't tell you what equipment you need. Manual J tells you how much heat the building gains and how much moisture the building gains and how much heat the building loses. Manual S tells you the right way to figure out what the equipment is capable of. And your job as a designer is to match those up. There is no such thing. Since we know that a 3-ton unit might be giving me somewhere between 26,000 BTUs and 40,000 BTUs. What is a 3-ton load, right? It depends on the context of the application, right? As for indoor and outdoor design temperatures, the indoor design temperature in Manual J is a recommendation. Manual J actually allows you to use different indoor design temperatures. The energy code, the people who are worried about electric use, are the ones who are dictating what the temperature has to be for designing an HVAC system. Manual J actually allows for some accommodation for homeowner comfort preferences, but the energy code does not. So that puts inspectors in a really tricky situation, right? When you have multiple codes trying to dictate the same thing. But I'm going to leave that to you. But the Manual J, which is the standard, the American National Standards Institute standard for how to properly calculate a load on a system, does allow you to incorporate customer comfort, but it doesn't allow you to choose any indoor design temperature you want. There are ranges and guidelines in the book that are slightly more complicated than a quick answer. But 75 degrees for cooling and 70 degrees for heating, with 50% relative humidity for heating, for cooling, and 30% for heating, are the average recommended design set points. If you are in far west Texas or north, it's mostly far west Texas. If you're in an area where it's your desert conditions and your coils are dry, then you use 45% for humidity instead of 50. But there's only a very small pocket of Texas where that's true.
I mean, as a code official, it's, the energy code is going to tell you 75 indoor, and a builder building a custom home is going to turn in a Manual J where his client insists that he wants it 65. And yeah, you kind of are in I've got the Manual J. This is what the guy wants. It's per the Manual J, but the energy code says 10 degrees difference. That's
that by the way, that 10-degree delta T thing that's BS. It's one thing to say you need to be able to maintain 75. It's another thing to decree what the split is, right? Because outdoor temperature should affect the split. Hot areas are going to have a bigger split. I will say this. One of the restrictions of Manual S is that you're able to look up real performance data of the equipment. Most manufacturers do not publish indoor performance or performance data with indoor temperatures below 70 degrees. That's my floor. Okay. I can't even tell you what this system will do below a 70-degree, 59-degree split. Dry bulb, wet bulb combo. So if you want to design at 68, I'm going to wash my hands of that, right? As a contractor, as an inspector, as a whoever, because I can't even tell you what the real performance of the system is at that temperature. And actually writes off software, which can automatically select equipment properly, will fail if you bring your indoor design temperature to 68, because none of the manufacturers provide us data below 70.
Why does AHRI pick numbers that aren't real?
They're real. They're maybe not realistic, but they're real.
Okay.
So I don't want to. I'm gonna plead the fifth on that one.
Okay, fair enough.
Anything I answer is speculative and not very kind to a partner of my parent company. So that's a bad idea. So
we'll leave that one alone. A few more questions. If all your ducts are the same size, if you don't have the velocity to push the air through, should you check the static at the register?
If all your ducts are the same size.
Understand that exactly. If all your ducts are the same size and you don't have the velocity to push the air through, should you?
It's not about the velocity to push the air through. Again, I'd recommend the residential duct design is backwards presentation, but I'm going to give you a brief glimpse of it because we're throwing around terms that are just a little confused here. If I look at that presentation. Right, there's pressure and then there's friction, and those are crying out loud, there's pressure. I'm on the wrong screen. There's pressure and there's friction, and those are the oppositional forces. So if you can't move the air, it's not because you don't have enough velocity, it's because you don't have enough pressure. And when you're talking about pressure, there's actually two kinds of pressure. There's velocity pressure and there's static pressure. And so if you don't have enough velocity, if you're not moving enough air, it might be because you have too much friction, not too much static, too much friction. And that's causing, all the friction is causing the energy to be used to push outward instead of pushing forward, which means there is a high static. And so, but it's, if it's not pushing air, it's not a lack of velocity. Lack of velocity is not a thing, right? Lack of energy, lack of pressure, yes, right? And so if you don't have enough energy, you don't necessarily want to check static at the register. You want to size your ductwork better. But the biggest downsides to ducts that are quote unquote too big are heat absorption. Right? It's surface temperature of the duct, right? Because the slower the air goes, the more time it spends in contact with the surface area of the duct, and the larger the surface area, the more heat absorption there is. So those are the big downsides.
With R8 insulation and 140-degree attic, that could be significant.
Yep, absolutely.
A couple more. Just completed a commercial office job with ducted returns in all offices. Engineer specified return air dampers. Why and how do you adjust?
Well, I don't want to speak for the engineer, but room pressurization is a thing that can happen positively or negatively. And so a lot of commercial jobs require full air balancing. And if you can have rooms that are pulling more, like you can have a pressure imbalance, meaning that there's more return than there is supply. That's not usually the problem. And when you think about residential systems, the not enough return is by far your biggest problem. And lack of return grills is another big problem. So we don't often think about what would happen if I had too much return in a room. But what can happen is room to room air imbalance, right? Where I have a higher pressure supply and a lower pressure return. Forget about airflow for a second, just think of pressure. Then that room is a net negative pressure. And that means that when it comes to infiltration, you can have the building drawing in air at that point, and that affects the overall pressurization of the building, and then it affects the overall, when you start pulling in moisture, or actually start pulling in vapor, you start pulling in air from the outside, which contains moisture, and it can do bad things to the building. So it's a little anal to balance return with supply, but with high enough pressures and large enough buildings, you don't want to create those pressurization issues because it can have an impact on the overall performance of the building. So my guess is it's about room pressurization. But again, I don't want to speak for that engineer. That's a guess. Your better bet would be to ask them.
Okay, two more and then we're done. I thought we're a little over. Thanks for sticking on with us this morning, everyone. Why does Manual J software upsize the heating and cooling loads by 20%, among other reasons, requiring the designer to stipulate system SHR so it can convert the sensible load to tons, ignoring the manual S procedures? I don't know if this is also, all equipment manufacturers' charts add more to the problem with the guessed SHR at 0.7 to 0.75 instead of the real one.
Okay, no. Okay, so that's that's slight commentary there, but they're on a point. The second half of that, they're missing it, but the first half, you've got something, right? So in RightSoft, for example. And we're not the only ones that do this. We will take a load. So let me just grab one that I'm doing in my class this week. And we will estimate the tonnage, right? And actually, I wish this was a larger load. At the lower end of the spectrum, this actually works really well. But if this were a bigger, I don't have one that I can just grab real quick. But so we use this estimated tonnage. So I see it too. I see the word required here. We phrase this poorly. To an engineer, this makes total sense, by the way. Required total cooling capacity at sensible heat ratio 0.7. The word at means assuming, right? In engineer speak. And so that's what this is saying. Is it assuming that your system, not your load, your system has an SHR of 0.7, then you would need about 1.8 tons, assuming 12,000 BTUs in a ton. Look, if we told everybody this was their load, how many plan reviewers, how many contractors, but how many plan reviewers too, would think that you should take these two numbers, add them up, and go look at AHRI? Ballpark, percentage, right? 80%, 90%? A lot, right? It'd be a big number, right? And that would be incorrectly sizing the system, and it would be consistently undersizing the system because AHRI is using test conditions that are inflating the performance of the system versus what a lot of us consider to be quote unquote normal conditions. Now, in some areas it would be closer, in some areas it'd be way off. Like Arizona would be a nightmare, right? And so we use this sensible heat ratio, which by the way, we didn't invent. We took this from the Manual J7 as a way of estimating tonnage or estimating equipment size if you're not doing manual S. Now, the right way to do it is always manual S, and your code enforcer should be looking for manual S reporting. And when you use manual S in the software, and I go and I use this select equip button here, I can get the program to look at the actual extended performance data of the system. And we will size it. We're not adding anything here, guys. The load is the load, right? And when I size this for manual S, we're going to find a matchup that with their extended performance data, because Microsoft has, so like all of the ones in red here, let's see, hold on. Sorry, when I turn this on, it has to do a lot of math. It slows down the computer here. I got Amana, AirQuest, American Standard, Arco Air, Bryant, Carrier, Comfort Maker, Daikin, Day Night, Goodman, Heil, Keep Right. We don't have Lennox, Ream, Rude, Tempstar. There was one up here, Smart Comfort, and Train. And we also have York and their subgroups and Nordyne and their subgroups, but you have to have a branded version of the software to use it. All of those brands, we can check this little box. We can select a piece of equipment that comes up. And when we do, here, actually, let me go and grab the evening class because that, I don't feel like looking for it. I was showing the class what happens when when you're in a situation, because this can happen, where the manual S rules don't really work for the current application, but we were able to make a selection here. So if I use the select equipment, what we do is we crunch these numbers. All those performance data numbers, all this, right? We take all of that data and we crunch it down and we actually select the right size system. And do you know how often that system matches the estimated tonnage if you're willing to take it as an estimate, right? So if this says 2.1, it's not a 2.5 ton, right? Yeah. It's probably a 2, but you have to be careful how you pick that 2. And I'll tell you what, there's 2.5. Like there's no such thing as a 4-ton load or a 5-ton load, particularly those 3.5 ton loads. So there's there's some folks who like to bash RightSoft, and there's folks in the energy world in Texas in particular who I've had conversation with, and they swear they're not saying this, but I get a million questions about how we oversize. So I don't know, 50 million Elvis fans. The thing that they say is, hey, here, look, and they do a load and they say, look, it says 5 tons, right? And they'll look at the bottom of the page and it estimates the tonnage at 5 tons when they look at this, right? And it'll say 5 tons. And then they'll look at these two numbers here, and then they do this weird thing where they say, look, the sensible heat ratio of the building is 0.85 or something, right? And they say, if we use a 0.85 as the sensible heat ratio, see, it's supposed to be 4 tons. That's not how that works. Sorry, I get a little mad with this one. That's not how that works. If you match the sensible heat ratio of the load to the sensible heat ratio of the equipment, all you're doing is adding up your sensible and latent and dividing by 12,000. That's all you're doing. You're doing the worst math, right? You do not match your sensible heat ratio of your load to your system. That is a shortcut for people who are good at math, who are looking at different matchups. It's literally a holdover from the literal chart and book days. So if you were flipping through your charts and looking for a unit and you knew the load sensible heat ratio was 80%, you would flip through and try to find systems that were around that 80% mark because it would be easier to match them up, right? Doesn't have to be exactly 0.80, but it would be in that ballpark. And that way you'd have a good split and good match. But the sensible heat ratio of the load doesn't determine the sensible heat ratio of the equipment. This equipment, right? And by the way, this equipment sucks at moisture removal, right? If I put this under Texas conditions, 105 degrees, 75 degrees, I'm not telling you who makes this equipment, by the way, 11% of this system's energy is going to be doing moisture removal. And if I have a load that's 20% latent and 80% sensible, that doesn't change the fact that this unit only spends 11% of its energy removing moisture. This unit will not work because it sucks at removing moisture. It's not, the ratings tell me that, but this is independent of what the load is. The load tells me what my building is. The equipment tells me what the system can do. My job is to match them up. And if they don't match, then they don't match, right? Setting them to match is like pretending all BTUs are equal, and they very much aren't. The right process is manual S, and manual S is not about SHRs. Manual S is about the percentage of BTUs. Manufacturers publish data using SHR, but you take that number and you do the math, right? And so I would take this 29,600 BTUs and 29,600 BTUs times 0.89 under these conditions. I don't care what your load is. These are the conditions it operates in. This is what the sensible capacity will be, right? 26,344. So you write that down. 26,344 is my sensible. And if I subtract that, because I can do this flipping the math around, it's going to give me a negative number, but that's okay. Whoops, that shouldn't have been a period there. 600. And so my latent is 3,256. So I have a sensible capacity of 26,000 and change and a latent capacity of 3,000 and change. If you have a load that was, let's say, I don't know, 25,000 sensible BTUs and 4,000 latent BTUs, that would work out to the right number of BTUs, right? 29,000 and change. You'd be right on the money. The problem is you have a 4,000 BTU latent load and you have a unit here that can only do 3,000 BTUs of moisture removal. You put this system in that house, moisture is going to build up every hour of every day. It's going to have mold. It's going to have all of the bad things that happens, even though you sized it based on manufacturer performance data, because you didn't look at sensible and latent as separate numbers. There is no magic SHR. Doesn't exist, right? You can't take the one from the load and plug it in. You have to look at the performance data, find out what this system does under these conditions. And it's confusing. I know it sucks, right? Because some manufacturers print total and sensible, some will give you total and SHR, but the SHR is just a mathematical way of telling me what the system can do. And what the system can do under these conditions, which are normal Texas conditions, is 26,000 BTUs of sensible and 3,000 BTUs of latent. And if that doesn't meet your load, then it doesn't meet your load. It's the wrong system. I don't care what the tonnage is, right? And the weird thing is you can, because there's room for sizing, right? You have to be within 15% of your total, 15% of your sensible, and 100% of your latent, or more. And so you'll have load calcs that could go with a 3.5 and meet the manual S, or could go with a 4 and meet the manual S, depending on how you match the coil and adjust the airflow, right? There are loads where a 3.5 ton is the right size and a 4 ton is the right size, depending on how you match that 3.5 ton and that 4 ton, right? And this is, so you want an hour on this, go watch There's No Such Thing as a Ton, where we get deeply into that. But this is a really, really big deal because there's like bad information out there saying that this is oversizing. So takeaway, don't look at this number on the project summary, right? Look for write-offs, so I can help you plan reviewers out a little bit. There is a report in the equipment section called the Manual S report, right? And we can look at the Manual S, and this is going to tell me that it's 107% of my sensible load, and then it's 142% of my latent load. And it's okay to be over on latent, but if you're under, you're toast. And it's only 114% of the total load. This meets Manual S requirements, right? But when you're looking at BTUs, not ratios, right? I don't care what that's, and by the way, this is a 75% sensible heat ratio for this system, but the load, and this is the one everybody looks at, and this is why people get confused. They look at this one. And so they look at the load sensible heat ratio. Let's see, I forget where the heck it is. There's the estimated, it's somewhere down here though. Load sensible heat ratio is 0.8, right? But even though the load sensible heat ratio is 0.8, this equipment, which has a sensible heat ratio of 0.75 or 75%, is still a properly sized system because it has enough latent capacity. It doesn't have too much sensible, and it doesn't have too much total. It's about the BTUs, not the ratios. All right. Yeah, I know that goes. I went off the deep end on that one, but it kills me when there's bad information out there and people pay money for a class to learn wrong stuff. It just drives me nuts. Sorry.
Dennis, I see you raised your hand, but if you could just type in your question, just send me an email with your question, and I'll be happy to, we don't typically unmute attendees on the webinars. We ask that you type in your questions, but I'd be happy to send Alex your question if I can't answer it myself. Just shoot those questions to me. I won't take any more anybody's time. We're a little over, so I'll let you guys get back to work or get back to, if you're me, homeschooling children trying to avoid drinking too early because this lockdown is kind of